Welcome to the second session. I hope recharge, as Neven told you. The subject is batteries, the core technologies. I am a moderator and my name is Željko Tomšić. I am from University of Zagreb, Faculty of Electrical Engineering and Computing. As a previous session, this session we start with 30-minute invited talk, and after that each panelist will be invited to give initial pitch for around 5 minutes. In panel, main speaker is Mr. Wu Kai, who is professor level senior engineer and the chief scientist of contemporary Amperex Technology Co. Limited. He has more than 20 years of extensive experience in battery research and development. He has spearheaded the mass production of China's first NCM lithium-ion battery and continues to maintain the technology leadership. In addition, has independently developed a key set of domestic battery manufacturing equipment which has achieved the leading position in the world in terms of efficiency, precision, and contingency in production. Please, Mr. Wu Kai.
Ladies and gentlemen, good afternoon. I'm Wu Kai from City of China. Many thanks to, Many thanks to Professor Mona for his kind invitation, and also to Professor Tomšić for your kind introduction, and also to Professor Li to recommend me to be here to give a speech on behalf of the Chinese Academy of Engineering. Today, my topic is battery applications in transformation of energy and transportation. First, sorry to say, I'm not good at English, so I have to put down my English words on the card in order to make my speech more smooth. You know, our company called CATL is a company to make the EV, electric vehicle batteries, and also energy storage batteries. Brief our company. Last year, our EV battery market share globally 37%, and already number one in recent 6 years. Similar to energy storage batteries. This is our company. Okay. Sorry. See, maybe I use the keyboard, right? Okay. Yeah, it don't work. Sorry. Okay. Restart? Yeah. The keyboard is not working. Okay, I try. Okay, it works. Today, I would like to discuss battery technologies and their applications. I will focus on these 3 sectors. The first is clean energy and transportation electrification. Second, the key to sustainable energy transition. And third, battery technology innovation. In response to climate change, the world is accelerating the energy transition. Until now, more than 150 countries have committed to a carbon neutrality plan, which involves 80% of the global CO2 emission, GDP, and the population. Based on the IEA report, more than 60% global CO2 emissions came from the energy generation and transportation. Emissions continue to grow. As we recovered from COVID, fossil fuels still play an important role in our society, posing a challenge to meet global climate goals. There are several methods to phase out fossil fuels and reduce carbon emissions, such as building a diversified energy supply, enhancing the grid infrastructure, and increasing end-use electrification. IEA suggests that electric vehicles will play an important role. By 2030, the global electrification rate will reach 60%. By 2035, 50% of sales of heavy duty trucks will be EVs. And by 2040, 50% of aviation fuel will be low-emission fuel. Then the next topic, the key to the sustainable energy transition. So, what is the key? The key is the keyword of my speech, battery. At least I believe, at least. At the grid level, batteries can store excess energy generated from solar and wind, which are intermittent by nature. Then, when energy demand is higher than renewable output, batteries can be discharged. This means that we can supply energy at night, with PV at night, or no wind is blowing. Batteries installed in electric vehicles can also play an active role in stabilizing the grid. This concept is called vehicle-to-grid, or V2G. This name, or V2G. The energy system in future will be mainly powered by solar and wind energy, nuclear power, hydropower, and other non-fossil fuels. In addition, distributed energy, namely energy production on the user side, will be an important supplement. While a battery in a single electric vehicle could be relatively small, an EV fleet can generate megawatt to gigawatt of electricity. V2G pilot projects have been carried out in several cities in China, such as Beijing, Shanghai, Chongqing. Customers can benefit from this. The importance of battery performance speeds up the electrification process. In the past 10 years, the specific energy of LP battery cells has increased from 100 watt per kilogram to 195. The specific energy of NCM battery cells has increased from 125 to 300. The power density has doubled to tripled. The cost has decreased by 80%. And the charging speed has increased, reducing the charge time from 8 hours to 10 minutes, from 10 to 80% state-of charge. The progress of batteries has also helped electric vehicles to be recognized by customers, and the penetration rate has increased year by year. In addition to the field of passenger cars, the electrification process of commercial vehicles, industry vehicles, ships, and aircraft is also accelerating. CAETS has helped electrify more than 200 ships of various types, and is also participating in the joint development of electric aircraft. In the process of helping the transformation of energy and transportation, it is very important for the sustainable development of the industry to establish production, use, cascade utilization, recycling, resource regeneration, as soon as possible. In the recycling process, metals such as nickel, cobalt, copper, aluminum, and lithium are recovered and kept in the battery value chain to manufacture new active inactive materials. Also, here's we call battery swapping. Battery swapping has also been considered as an alternative and valuable business mode in addition to electrical vehicle charging. Battery swapping can also benefit and enable battery reuse. These batteries are managed in a unified way and retired in batches. And at the same time, volumes of end-of-life batteries for recycling become more predictable. Having a battery traceability system, okay, is important to provide transparent and reliable information regarding the battery lifetime. Why this? This is just because the battery is so important. We need to differentiate each battery pack and cell. We need to differentiate. Then how to do this? We need to differentiate. Then how to do this? This just like ourselves, every person. I make an example. How can I easily come from China to Croatia today? That's just because I have my passport to differentiate. I'm Wukai, but not you. So the Croatia customs can let me enter in. I'm Wukai. I have my age, my nationality, a lot of information. Then can differentiate in the world so many people, but only one Wukai. So for the battery, the same. CATL has set up the passport for all battery cells and packs. Here's an example. Okay, you see the CATL battery passport. This is a battery pack. This is a passport number. And here you see this battery pack, carbon footprint. Okay, from this, just we scan the QR code on the pack, we can get this table. Okay, so for this carbon footprint, from this number, you can know whether it is compliant with the European battery regulation or not. For example, here, recycling materials, it can tell you in this battery bag how much recycling materials are be used. So a lot of information here. So this can differentiate this battery bag, the unique in the world. Only this pack. So in recent years, we saw fast development of battery technologies. So for the third part, in the following slide, I would like to share some of our key innovations and achievements. Batteries for stationary storage and electric vehicles have different performance requirements. However, safety is paramount, always number one, no matter EV, no matter energy storage. In addition, other main requirements for the energy storage are life and RTE. RTE means round-trip efficiency. Okay. And for the EV battery is the high energy density for increasing the driving range, and also fast charging capability to reduce the charging time. This is very key. In terms of battery safety, safety is always number one. We need to avoid, very important is thermal propagation. So what is thermal propagation? Thermal propagation means in case one single battery cell thermal runaway. The rest of cells in the pack fail one by one. We call it thermal propagation. That is not acceptable, because if thermal propagation happened, you can see fire outside the pack, even explode. This cannot be accepted. This is why CATL developed the so-called no propagation or NP technology. Here we define the 4 generations of our NP technology. Passive protection, just do some protection. Active isolation, control of smoke gas, and for the failure in perceptibility. These are all the 4 stages. Today, we are on the stage, the generation 2, NP generation 2. We call it the active isolation. This is the second generation technology achieved the high voltage and smoke isolation. This technology compatible with different battery chemistries and voltage platforms, and it has already been deployed in mass production already, this year already. For safety, besides the design, the manufacturing process is also very important. High quality in the battery manufacturing will lead to increased safety at the battery pack and the application level. A car contains dozens to hundreds of battery cells. And the ppm level cell failure rate will lead to a car failure rate in 1 out of 10,000. You know, if 10,000 cars, 1 car will fail, maybe have fire. That cannot be acceptable. But where this number here, because tens of years ago, in the cell phone, the notebook, that kind of the failure rate around 1 ppm. That can be acceptable, because our cell phone, only 1 cell, battery cell, only 1. But in a EV battery pack, hundreds cells. So still 1 ppm of cells failure rate cannot be acceptable. So thus, through a series of innovations, the single cell failure rate made by CATL can make ppb level, part per billion, not per million, per billion. And this vehicle level failure rate will achieve 1 out of 10 million. We can achieve that. Just by this achievement and also some others, we get our Yibin factory and the Ningde factory, 2 plants, have been awarded as the lighthouse. These lighthouse factories by the World Economic Forum, and they are the only 2 lighthouse factories in the battery industry globally. Only 2 by now. Just because of the failure rate is the first reason they gave us the award. Besides the safety, battery lifespan is a key requirement for both the stationary storage and also to enable V2G is very important. For achieving long cycle life, the side reactions and capacity fading during battery use have to be suppressed. For this, anode surface treatment and cathode doping and coating technologies have been deployed to minimize the side reactions. In the meantime, self-healing electrolyte, this is by CATL technology, self-healing electrolyte has been introduced to improve the cycling performance. In 2020, CATL supplied long-life batteries with 12,000 cycles for a 100 megawatt-hour energy storage station in Jinjiang, Fujian province, China. It has been running safely over 1,300 days and provided 1.2 trillion kilowatt hours of energy to the grid. The long-life battery technology provides a technical feasibility for the energy storage application. RTE, round-trip efficiency. This is a ratio of the discharged energy to the charged energy. We call this RTE. By reducing the cell resistance, or DCR, and the system impedance, and by implementing new technologies, such as intelligent state-of-charge calibration, we have increased the RTE from the initial 93% to currently 96.5%, greatly improving the competitiveness of lithium-ion battery for stationary storage. Super fast charging. The charging convenience and the charging time are affecting the customer decision to purchase the electric vehicles. Most people hope that the charging time could be as fast as the refueling of combustion engine vehicles. I think everyone very familiar with your combustion engine vehicles. Do you agree? I think sure you will agree. Why not? Sure. But you know, but you should know, from the technical side of battery fast charging is not so easy. Very difficult. For battery, very difficult. Then, how long time can you accept? How long time? For combustion engine vehicles to the gas station, within 5 minutes, 1 tank of gasoline, within 5 minutes. Now for EV battery, for EV car, by our market investigation, we have to do the market investigation. By our market investigation, for EV, 1 charge, 1 time, 400 kilometer driving range with less than 10 minutes charging time is acceptable. Our investigation. The best is within 5 minutes. So 10 minutes to 5 minutes, 400 kilometer driving range is acceptable. Thus, okay, we recently announced that, okay, our breakthrough technology achieving 4C fast charging in lithium-ion phosphate batteries. 4C charging means 10 minutes charge for a 400 kilometer range in 10 to 80% SOC window. We can achieve this today. For this the technology, new technologies of here, I showed, okay, some example. New technologies of super ionic conductor and nano-structured lithium-iron phosphate cathode materials have been applied to improve lithium-ion diffusion. For the anode, we have developed a faster ion ring on the material surface to increase the ion insertion channels and improve ionic conductivity. We also deployed a multi-gradient layered electrode to balance the fast charging and the high energy density during cell manufacturing. You know, for the battery cell guy, you should know fast charging and the energy density usually not easy to have both the increase, not so easy. So we do some balancing. And then next, we are now developing the product, 1 charge, 400 kilometers, with 5 minutes charging 1 time. Hope it will soon in the market. Maybe next year, CATL have the plan. The improvement of the energy density of EV battery can greatly improve the range of electric vehicles, the driving range. And the chemistry is crucial for increasing the energy density. We continue to develop and use materials with high specific capacity as the anode and cathode materials for the battery. Anode cathode material for the battery. This is our the chemistry, the energy density roadmap. Okay. With our proprietary condensed battery technology, this is our CATS technology, we are able to achieve ultra-high energy density for aviation application. Just for EV, this is for aviation. So for EV battery, currently the highest the energy density for battery cell is around 300 watt-hour per kilogram. That's not enough for the aviation. Aviation usually we need 450 kilowatt-hour per kilometer. That's the number at least. So we do this development. This one is by integrating a range of innovations, including a highly conductive biomimetic condensed state electrolyte, an ultra-high energy density cathode material, an innovative anode material, and also thinner surface treated separator, and also advanced manufacturing process. This one, we already, this end of this year, we can put it in mass production. The only shortcoming of this battery pack, the shortcoming is the cost is very high currently. But we want to, okay, in the near future, want to reduce the cost, but currently very high. This is one technology for high energy density. Another one is we call the metal-free battery. We also developing this one just from a non-transition metal cathode material. You know, current our cathode material, for example, NCM, because lithium, we have nickel, cobalt, manganese, all transition metal. That the cost is high. So we just want to develop a non-transition metal cathode material through our high throughput calculation. You know, we have a laboratory, a lot of guys to do the high throughput calculation. We need to do the calculation, expecting to get the energy density beyond 500 watt-hour per kilogram with a very competitive cost in the near future. This is what we're doing. And currently, we have already do a lot of calculation and in the laboratory, we get the gram level some sample we have already got. In addition to the above technologies, I would like to share some progress of the solid-state battery in CATL. You know, solid-state battery, just you know, almost every the battery company and university doing this. Okay, solid-state battery. So I have a general intelligence for the progress of CATL. You know, for this, the utilization of lithium metal anode is a key challenge. We need to use the lithium metal. So why not the all solid? If still use the graphite, is no meaning. So we need to use the lithium metal to increase the energy density. But with in order to use the lithium metal, we have to use them all solid. Okay. That one, you know, the challenge is because of the lithium dendrite. This is a big challenge, which can lead to the battery failure and safety issues. CATL has engineered an advanced electrolyte interface. By implementing our mechanical enhancement technology, we achieved a critical current density of 20 milliamp per square centimeter without observing any dendrite growth. Additional challenge is improving the solid-to-solid contact. Solid-to-solid contact, because all solid in the cathode side, the cathode material particle, when discharging, is shrink. The solid electron and the particle, the interface may separate, that the impedance will be very high. Okay, it cannot be used. So the solid-to-solid interface is very, very important. For this one, CATL has developed a mixing conduction network technology, greatly enhancing the cycling stability of solid-to-solid interface, achieving over 6,000 cycles under 3C conditions. Still, this one is just in our laboratory, not in mass production. To the mass production, still, I think, in some time. Another way to improve the energy density of EV batteries is structural innovation, which helps to further improve the energy density of batteries by improving the volumetric efficiency in the battery pack. Okay, this is the C2B, generation first, second, and third. What is a C2B? Traditional battery pack, we use battery cells, make a module with 10 or 12 or 20 cells, make one module, and put all modules in the battery pack to make a battery pack. Three steps. But CATL, we have the innovation. Okay? We just put a cell directly in pack, no any module. So this we improve the volumetric efficiency. This is what we call C2P, 1, 2, 3. And future we planned, we call this CAETS, is a CATL integrated intelligent sensing. This is a EV platform where integrated all the key components such as battery system, DC-DC converter, onboard charger, the electrical drive system, the thermal management system, as well as the vehicle sensing, just integrate together. The efficiency will be very high. Okay, this is the future. Okay, all our Academies solution. Today, the 2023, our up-to-date technology is C2B generation 3, or we call this Qilin. For the Qilin battery, okay, let me explain more. CATL's Qilin battery this year already in mass production in the market. Qilin battery is the third generation of our cell-to-pack technology. A multifunctional cooling plate here, okay, not so clear, okay, sorry, is sandwiched by the two larger surfaces of two neighboring cells. Our cells is a hard case cell, okay, two neighboring the face, okay, in between we sandwich the cooling plate. This cooling plate possesses three functions, not only one function, not only cooling, but three functions in one cooling plate. The first is the cooling function. The second is the thermal insulation function. Just talk about the NP, no propagation, by this. The thermal insulation function. And the third is swelling absorption function. Because our battery cell charge and discharge, the thickness become large and small. Okay, when charging, we are swelling. So this one also can absorb the swelling, this function. So three functions in one. This pack design reached a record high volumetric efficiency of 72% and energy density up to 255 watt-hour per kilogram. A Chinese brand vehicle has been produced with a range of over 1,000 kilometers by using this technology. This one, okay, put here, you can see our Qilin battery was recognized the best inventions of 2022 by Time. The best inventions, 2022 by Time. Battery applications are incredibly diversified, and there is still significant potential for performance improvement. Well, currently, lithium iron phosphate and layered oxide batteries are dominant in the market today. Still, here you can see the MCP battery, sodium-ion battery, lithium metal battery, some other copper-free, some cadmium battery, some a lot of others. Okay, others is technology, and some other technology pathways still have unique performance advantages. With the expansion of battery application and the deepening of segmented markets, more technology pathways will be commercialized, I think. The year of new clean energy is coming. As a battery provider and supplier, we work closely with our customers to achieve safe and long cycle life batteries for stationary storage, safe and fast charging batteries for vehicle electrification. Ultimately, to unlock the door to energy freedom for society and humanity. Thanks.
Thank you very much for a very optimistic perspective of batteries. Now we will continue with our panel, and I will invite our panelists. First is Tony Harper. Tony Harper is Challenge Director for the Faraday Battery Challenge in UK Research Innovation. He is responsible for the UK government £500 investment in scientific research, business-led innovation, and national scale-up infrastructure for battery technology. Tony is fellow of the Royal Academy of Engineering, chartered engineer. Second panelist is Zoran Mandic. Zoran Mandic is full professor at the University of Zagreb, Faculty of Chemical Engineering and Technology. He has a background in electrochemistry and electrochemical engineering fields. In the last 10 years, his work has focused on development of advanced electrode materials for energy storage application, particularly batteries and superconductors. And the third is Mario Vašak. He is full professor with the Department of Control and Computer Engineering at Faculty of Electrical Engineering and Computing and head of Laboratory for Renewable Energy Systems at FAIR. His current research interests include the domain of dynamic system predictive control with application to buildings and infrastructure. Now we will continue with short presentation of our panelists. Mr. Harper.
Right, luckily I only have one slide, so hopefully the technology won't fail us. So I'd like to start by sort of introducing you to some work that we've been doing in the UK. So like many countries, we have been looking at how many batteries we need to support primarily our automotive industry. So I'm not talking about the market here or about EVs on the road. I'm talking about how many cars we produce in the UK and what batteries, what number of batteries that those factories will need. So two numbers to stick in the mind to start with. One is that by 2030, we will require about 90 gigawatt hours per year of capacity, of production capacity in the UK. So you've heard a lot of facts and figures today, but 90 gigawatt hours by 2030. Actually, that's only about a tenth of all of Europe. So Europe requires obviously an awful lot more. By 2035, that 90 number rises to about 135. By which time the United Kingdom will be mostly making electric vehicles. So most of the car plants in the UK by 2035 will be making electric vehicles. And bear in mind that the UK exports 80% of its production. So all of the car companies are looking to the global regulations and trying to work out what their product plans should be to meet the global regulations. And as I'm sure you know, car programs take sort of 4 to 5 years in gestation, anywhere between 500 million and £1 billion per car program. So you have to plan ahead, and pretty much the UK car industry is committed. But this slide then looks at a further piece of work where we said this 90 gigawatt hours, fine, but are these batteries all the same? And the answer is no, as hopefully you can sort of infer from the slide. So there's a wide range of battery requirements, from small urban utility vehicles through high volume vehicles, through premium and sports cars, large luxury sedans. So we make Range Rovers, we make Bentleys, we make Rolls Royces in the UK, all the way through to supercars, McLarens, Aston Martins, and so on. And so we did a piece of work to essentially try and define what the pack level requirements from an energy density point of view, gravimetric and volumetric energy density are. And we could do that because we could reasonably well foresee into 2030 what vehicles would be made, what size those vehicles would be, what weight classes those vehicles would be, what the customer requirements of those vehicles would be. And to cut a long story short, you can sort of almost, design the vehicles and design the battery packs that need to go into those vehicles, and then sum them up, which is essentially how this piece of work was done. And then once you've done that, you can overlay the pack level capability envelopes of various battery chemistries. So you can see that we've overlaid an LMFP capability envelope, and then one for NMC as well, which I think the figures tally reasonably well without any kind of pre-discussion. The figures kind of line up. So what I'd like to do is just make a few remarks by sort of taking a tour of this chart, really. So the first thing to note actually is that for if you look at the orange block there, 18 gigawatt hours and the supercars, actually the customer-driven requirements of those vehicles lie outside of the capability envelope, even of the very best batteries that we have available today. And so what that implies is a few things. One is we need to keep pushing the capability envelope of NMC, and you've seen earlier some of the technologies that can push that both at the cell level and the pack level. And I think we'll also see some dialing back of some of the customer requirements. So for Range Rovers and Bentleys and so on, some of those vehicles won't quite have the range that customers might expect. For supercars, you can see that at the moment they're laying well outside of the capability envelope, and I would say that's companies like Rimac are trying to solve that problem, but also that's why a number of those companies, I think, are arguing for a small volume derogation for e-fuels and so on, because it's very, very difficult to meet their customer requirements with batteries alone. The other thing that becomes obvious and was a slight surprise when we did this, although I think it's well known in China, is that a large amount of the volume requirements here can be met by LFP, lithium iron phosphates, or lithium manganese iron phosphate. And that means that actually, but today, certainly in the United Kingdom, and I think to a certain extent in Europe, most of the production capability or capacity that's being installed right now is all high nickel. So you could argue we are sort of over-engineering our manufacturing capability here on this side of the world, because a lot of the cars and vans that we make could actually be catered for by lower cost materials. And bear in mind, LMFP doesn't contain nickel or cobalt, so it would take a lot of the strain off of some of the materials as well. So it'll be interesting to see how that plays out over time. The other remark I would make in that sort of middle of the chart there is that cost is king. Over time, to get the user acceptance and to get products and smaller. Somebody earlier talked about smaller products with cheaper batteries. Absolutely possible. But also we need to drive down the cost of manufacturing. So we need to, that's why every company is looking at dry electrode coating to stop the energy, or to get rid of the energy that's used for drying electrodes. But also, clean and dry rooms in gigafactories take up huge amounts of energy. So finding ways to mitigate mitigate those processes, and also looking for other manufacturing energy efficiency improvements. So there'll be a lot of innovation to be done to drive costs down in the middle of that chart. You've just heard about extending the capability range of the NMC box. So the way I would characterize that is that there's not immediate breakthroughs, so some super cool thing that's going to come along and completely transform it. Although maybe we'll talk about more transformative technologies later. But as you've just seen, a continuous drive to improve energy density at chemistry level, at module, well, maybe getting rid of modules, and at pack level, and with software as well. And as I say, I would characterize those as incremental improvements, but they require breakthrough engineering. So adding silicon to anodes, for example, you think, well, that increases the energy density, so why not just add silicon to anodes? Well, silicon expands when it's charged and discharged. Expansion is not something that you want, and expansion and contraction is not something you want at a cell level in a car battery. So the challenge there is to engineer the material so that the silicon can expand at the atomic level, but it doesn't expand at the macro level. Some great scientists are doing that, but it requires breakthrough engineering, not only to make that happen in the laboratory, but then to be able to make whatever the solution is, to be able to make tens of thousands of tons of that material, and then for that material to be compatible with the processes that are in gigafactories all of that requires breakthrough engineering. So everything that you've heard here requires breakthrough engineering, even though on the face of it it's kind of incremental. I've put a couple of benchmark examples on here, and sorry, I've used the NEO ES6 example, which has, I think, a Li-ion battery in it as a concept, not a CATL battery. But again, that concept is driving gravimetric energy density to around about 260 watt-hours per kilogram. So in there is all of the things that you've just heard of: high silicon anodes, semi-solid state, electrolyte, nano-engineered, very, very high nickel cathodes. And so, again, just echoing what's been said before. The other benchmark I put on there was the Mercedes EQXX concept, and that just echoes, again, what we've just heard around. Most of that volumetric energy density comes from getting rid of the module level, so going straight from cell to pack, but also going to passive air cooling rather than liquid cooling. So that gets rid of a whole load of other pieces of engineering that are required. But in order to do that, you have to engineer the vehicle in such a way that it's highly efficient and drops the power, the transient power load on the battery. So briefly, I've also put on here where the overlaps with other sectors are. So at the bottom, actually, I did a bit of Googling when somebody asked about vanadium flow batteries, and I discovered that the flow batteries are about 20 on volumetric and 20 on gravimetric. So they're sort of way down in the bottom left-hand corner of this chart. So not great for car applications. But anyway, at the bottom left of this chart, I think there is a real opportunity of overlap between automotive and stationary storage, and potentially a good introduction point for new chemistries such as sodium ion, which have got the opportunities again to be cheaper and to take the strain off of some of the material supply chain. At the top right, you'll see that in principle there are overlaps between all-electric flight and the supercar requirements, and that might also be a good entry point for lithium sulfur, although I would say lithium sulfur is still in the lab. It has issues when you charge and discharge it. It tends to pollute its own electrolyte, which is a big scientific problem that needs solving. And I put in where I think is a likely market introductory point for solid-state batteries. And I'll make a sort of a more of a market comment rather than a technical comment on solid-state. And that is because it's going to be expensive in the first instance, it's going to have to come in at a very, very high performance level at a place where the price elasticity is quite good. The only thing that will drive down the price of solid-state batteries is high volume, and the only way you get to high volume is if you can start somewhere on that chart and then generate volume. So if you come in too low, if you come in the NMC or God forbid the LFP box, nobody will buy it. Even though it's solid state, nobody will buy it, and we'll never get market penetration of solid state. So there's a market issue with solid state as well as all of the technical ones. And so the only other remarks I'll make before I close are I would absolutely echo everything that's been said about recycling. We need right across all of these applications, across all of this volume. We need recycling, and we need the battery passports that have been talked about earlier. We need, I think, also to look at all of the breakthroughs that are happening in digital right now, be that machine learning and other breakthroughs that are happening, and see how those can be applied. I think I got a hint on the material discovery for that cathode earlier that you may be using machine learning to do the screening. You know, all of that kind of technology needs to be looked at to see whether it can be applied. And the last comment I would make is around skills. So the comments I made, for example, around what you need to do to get to high, to stretch that NMC box, you need to be looking at the mechanical engineering, the electrochemistry, the software that controls the batteries, the thermal engineering, maybe even the vehicle engineering, the aerodynamics and the weight and the efficiency. You very, very rarely find all of those disciplines in one engineer, yeah? But we're going to need them, yeah? We're going to need a lot of very, very highly skilled, cross-disciplined engineers to drive this forward. And with that, I'll close my remarks. Thank you.
Thank you very much. Good evening, everybody. I would like first to thank Neven for inviting me here, which is my great pleasure to be with you and to give my view on the battery cells situation today. So we are all well aware that lithium-ion technologies are, in fact, a key technologies enabling the present state of the electric vehicles as we know it today. Lithium-ion technologies were invented in the late 70s, early 80s, and then commercialized in 90s in electric vehicles. But it's obvious today that the development of the lithium-ion batteries does not keep pace with the requirements from the electric vehicles, which are ever-growing and which keep going up every year. So what is in fact the problem? I mean, the problem is what has already been mentioned several times here, and what we've heard from the Dr. Kai and Professor Harper. Then there are several performances and several properties of the batteries on the cell level which affect slow development of these batteries. One problem is with driving range, which is closely related to the energy density. Another problem is the charging time, which is related to the power density. And finally, the cycle number, which is related to the reversibility of electrochemical reactions taking place inside the battery. So all these performances, which are not quite good today on the cell level. And the question arises what we should do now to improve the cell level and what directions we should follow to be able to meet these challenges and to ensure enough battery quality for the electric vehicles. So there are a couple of directions which we could meet, and there are a couple of challenges which we should face. First challenge, which is the relatively slow progress in the development of these batteries. What I mean under the slow progress? Let's say that from the early 90s, when the battery lithium-ion technology was commercialized. At that time, we had a lithium battery which, with the energy content of about 100 watt-hour per kilograms. Now, as we've seen in the previous slide here, we reached the energy content, energy density of these batteries about 200, 250 watt-hour per kilograms. So it's about 200 watt-hour per kilogram, which is for the LFP technology, which is the top energy density we might expect, and further increase we could obtain with another technology like the NMC technology, which is nowadays is tried to be avoided due to the ecological reasons. As a target, and everybody is considering that as a target for the energy density of the battery cells today, and as European Commission put it, for the battery cell to be sustainable and to use it sustainable in electrical vehicles, the target of the energy density is about 400 watt-hour per kilograms. So we are far, far away of this target at the moment from the practical view, regardless of very impressive number Dr. Kai showed us that we might have nowadays even higher practical energy densities today. But it's also, it belongs to the realm of the laboratory and the short-term usage, but for the widespread practical applications, I think that the more practical numbers are 200 to 250 watt-hours per kilogram. So in order to meet this challenge of 400 watt-hours per kilogram, we could do two things. We could wait for the incremental increase further, which might take up to 10, 20, or 30 years to reach. Or we could change our approach, we could change our paradigm, and try to replace the existing lithium-ion technologies. And what could be the direction for this paradigm change? What could we do to change these technologies? Today, we have, let's say, two possible directions. On the cellular level, what we should do and what potentially might bring us more sustainable and better technology for electric vehicles to be more usable. One is lithium battery technology, which is quite different from the lithium-ion battery technology. A lithium battery technology uses pure lithium as an anode material. And if we would be able to use anodic lithium as an anode material, we would increase the practical energy density. Maybe we could double it and maybe even triple it. But as you probably know, the use of the lithium metal as an anode is avoided due to the safety reasons of the reactions of the lithium, which might lead to damage and fire and explosion. As a part of the lithium batteries, using lithium metal anode, is also the technology, solid state technology, which is developed because of the possibility of using lithium metal, increasing energy density. But there is also another challenges with these technologies which are still to be faced and overcome in order to improve and to bring these batteries to the satisfactory level. Another challenge we are facing with the development of the batteries is because we have, when we want to improve one of the performances, for example, if we want to improve the energy density of the battery, as a rule of thumb, we deteriorate power density. We cannot, or at least it is not easy, to increase simultaneously energy density and power density, or cycle life, for example. So we should know what our application is in order to, on the cell level, increase particular property like energy density. If we want longer driving distance, we try to implement increase the energy density, but we lose on the power density, and charging time suffers. So there are different challenges which need to face, and hopefully in the future, and so much funds are invested, very huge funds are invested in such types of technologies. And another type of technology, apart of the lithium technology, would be going beyond the lithium ion and lithium technology as such. So a lot of research efforts today are made in order to bring new technologies and new metals into the perspective, such as, for example, sodium technology, sodium ion technology, or magnesium and magnesium ion technologies. The advantages of these technologies might be in the sense that we could use a pure metal as an anode, not intercalating ion, which loses energy density, which pays on the energy density. So there are a lot of directions which are now followed, and hopefully in the future, one of these technologies will be brought to the level good enough to be to be satisfactory for the battery, which would be used in electric vehicles. But we could continue on the discussion.
Okay, dobro. Sad nešto da vidim.
Okay. So, hello everybody, good evening. Thanks to the organization board for inviting me. So, as you heard that my background is control engineering, so I will try to contribute to this panel with a topic from the control engineering domain related to battery cells. And what I would like to emphasize is that the battery and battery cell and the battery pack is actually a dynamic system, and one of the painful properties is its deterioration with time, since we know that different behaviors of the battery are aging this battery differently. So it is very interesting to find what would be the allowable combinations of currents, voltages, and some inner states of the battery cell, which would make the degradation smaller. And when planning how to use the battery, to try to stick to those states, stick to those combinations of variables in the battery cell that actually make the degradation smaller and thus prolong its useful lifetime. So actually this is a common issue for all battery chemistries, and as control engineering perspective provided to it from the view of dynamic systems. So I won't be touching any specific chemistry, but at the end, the AI, what was mentioned in the title, is also here to actually provide a way to alleviate the modeling of specific degradations in different battery cell chemistries, and to enable finally that the specific computational procedures can be used. So what actually is the state of the art today when we talk about BMSs who are in charge to keep the battery fit for as long as possible? So for a given battery state, they try to find what are the allowable constant currents or constant powers that can be applied over a certain short amount of time to the battery, such that they are kept within certain limits. The idea here that is like an incremental step forward is to try to see for a specific battery state what kind of a profile of current or power can be applied over a certain short time ahead, such that the degradation is kept below a certain given threshold. And when having the battery cell model as a dynamic system, when having the battery aging described as well, we are, from the control engineering perspective, ready to do such things, to characterize actually what are the acceptable combinations of battery inner variables that will keep the degradation under given limits. So the idea is to have the battery cell represented as a dynamic system, and to have the degradation described as well, and introduce then degradation constraints. So the, let's say, allowed degradation speed of our battery. And now I'm talking about the procedure that can be performed offline, computed offline. So based on these descriptions by the computational geometry procedures, which we can characterize from one hand side the allowed combination of states, and from the other power inputs or current inputs to be applied as a sequence of actions over a certain short time horizon in the future, giving us finally the possibility to say to any system that uses this battery how the battery can be used safely to keep the degradation under a certain limit. Meaning that online, once such protective set is computed, you are allowed to evaluate the allowed set of actions. For instance, so this lower figure shows you that x0, being the current state of the battery cell, is assessed as a current estimate. And then for this current estimate, you are assessing here one-dimensional in this graphical representation, but actually multi-dimensional set of profiles that can be used by the system that is supplied by this battery, such that the degradation is kept below a certain threshold. So at the end, to make this procedure encircled, let's say that, of course, artificial intelligence and machine learning are very welcome, but in combination also with knowledge about electrochemistry, to parameterize the models properly such that the data can be used in the best possible way, and that the number of parameters needed for characterization of this model is low, such that finally the variance of such a model at the end is low. Then, of course, a specific degradation constraint can be set. It can vary, of course. It is a matter selection by a certain designer. Some sports car would probably be more modest in that sense, and some passenger car may be less modest and want to have, let's say, more strict these degradation limits. And finally, then comes the evaluation of such a set. So computational geometry procedure, which of course I won't be talking in any details here. And we are talking about battery cell all the time. Of course, we know a battery pack is a collection of cells. So at the end, in a battery pack, different cells are in a certain spread of states. And the robust and, let's say, a procedure that is cautious would be to take into account all such states of different cells in the battery pack, and then in an intersection of all these constraints to set which profiles are feasible to be applied. And this is online run as a sequence of multiple and dead instructions, so something that can be readily and fast evaluated once these protection sets are computed. So just a small perspective from the control engineering side, how we could help for different battery chemistries. So thank you for the attention.
Thanks for all panelists. And before the questions, I will ask the panelists if they have any comments to any of these presentations, because this was very different presentations, but if you have any comments.
Maybe I could start. I was really impressed with the numbers which Dr. Kai showed us with the technologies. I wanted to ask you, are these technologies of your company inside or your laboratory in China? The numbers you showed us. Yeah. These are the results are very impressive. I wanted to, yeah, okay.
Any other comments? If not, before the questions from audience, I will take my position to ask one question to all, short question. As I am power system engineer, and of course there is no question that electricity transition is going to renewables. But also, we know the one characteristic what is of electricity system is different from anything else. This is that each moment, supply and demand should be equal. This is the main characteristic, and for that, all this story about storage is extremely important. And my question is, when you mentioned something, but when you, by your knowledge, expected commercial utility scale battery storage, really commercial. I mean, you mentioned some, let's say, pilot project or something like this, but really large commercial utility scale storage. When you expect?
So, is this on? No? Okay.
No. Switch on.
Switch it on. Can you hear it now? Okay, thanks. So I can only speak from, again, the UK perspective. So in the UK, we have something called the national grid that looks after the grid. And in order to hit their sort of decarbonisation targets, actually some of the grid scale installations are already happening at pilot scale. And so I think it's about between 2030 and 2035, there'll need to be somewhere around 40 to 50 gigawatt hours of capacity, large scale installation done between 2030 and 2035. So just to give you some idea.
Professor Kai.
I don't answer the question. When will grid scale energy storage happen in reality in China, on a large scale?
In large scale, yeah, for Okay. For CTL, the last year, our iron storage, we have around 40 gigawatt-hour output. This year, we around 70. I think today, we already have some skill.
But is
Alright.
it commercial? I mean, not pilot project, really commercial that is feasible, not...
Yeah,
70 gigawatt hours sounds large scale to me.
Yes,
Yeah.
yeah, large, but
So today, I think already have a start already.
okay,
Not
thank
yet, but already.
you. Any comments? No vision?
As far as I know, Croatia has not, is lagging behind, but also in the future. I know that Varta wanted to implement here in Croatia some pilot storage facilities, but I'm not quite sure how far they gone in these directions. But let's say I can't say anything more about it.
Okay, thank you. Because in the previous panel, there was so much interest in batteries. And now questions from audience, please. It's coming.
Do you hear me? Hello, my name is Tomislav. I'm from Rimac Technology. So, one question for Mario Vašak. So, are these projects of yours commercial? So, if we, for example, come with some cell, are you able to give us the results? I don't know, in 6 months?
Actually, the last slide was just telling the idea what we are now trying to do with company Rimac. So still nothing commercial, still to be investigated, the whole sequence step. What was done so far is to validate that we can compute a protective set for battery cells and that we can evaluate it online efficiently. What still we need to do is to do the machine learning part for the aging model of a specific cell. And it's a part of a research project that we are just applying, so something in plans, let's say. Yeah.
Yeah, I mean, this is really important because this is something that customers are now looking.
Yeah, I understand.
Maybe
Yeah.
one of the most important things.
Thank you. Okay.
And one question maybe in general, do you know, working with many companies, for example, Mr. Tony Harper in UK, are those OEMs are moving towards cylindrical cells or prismatic cells? Is there any trend, or is it all application related?
Short answer, there's no trend.
No trend.
I think we're seeing all of it. So large format cylindricals, so 46XX cylindricals. So we're seeing less application of 21700 cylindricals. So cylindricals moving to large cylindricals. We're seeing perhaps more interest in prismatic than we've seen in the past. So I think there will be a significant amount of prismatic. Maybe, if anything, pouch cells we're seeing slightly less going forward. So, say large format cylindricals and prismatic.
Okay. By our study CATL, okay, pouch not good choice. Prismatic, the first one. Cylindrical, only some case, but mostly will be that, especially the large capacity one, will be the prismatic.
Other questions? And then here.
I have a question maybe for the first speaker, but for all the panelists as well. We see first design of batteries for electric vehicles able to drive 1,000 kilometers. On the other hand, we see also further improvement in the number of cycles battery can do. I was really impressed by the 6,000 cycles you presented in your presentation. And suppose you have an electric vehicle that can drive 500 kilometers. 6,000 times is 3 million kilometers for one vehicle. If you compare it with petrol and diesel vehicles, they can drive 200, 300,000 kilometers and then they have to be recycled. So what should be the design for new battery technology? Should we aim at having batteries driving 1,000 kilometers with 6,000 cycles or with only 500 cycles? Or should we aim to have batteries with a lot of cycles but maybe a lower driving distance?
It depends on depends on the application. By the technology side, currently, a CATL, we can already get the 80,000 cycles, 18,000 cycles. That's what we can get. But depends on the application. If you know some passenger car, private passenger car, so maybe 1 year only less than 10,000 kilometers. We do not need the long cycle life. Because if we get some long cycle life, we can get, but always or usually high cost. That means high price. So if we do the battery swapping, that kind of business mode, okay, long life, very good meaning, the swapping, time by time, okay, always be in use. So that's long life, very, very good. So we need the long life. For the energy storage, usually 20 years, okay, large one, only 20 years, so we need the long life. But for some the passenger car, for private use, usually we do not need a long cycle. So technically, we are kind of 18,000 cycles by now.
Thank you. My question relates to battery packs that consist of many cells. Can you help me understand how the malfunctioning or the poor functioning of one cell affects the others and what one does about it?
So there's quite sophisticated battery management software within battery packs and battery modules. So the state of health, state of charge, and other parameters of each of the individual cells is monitored in real time. And if and by the way, no two cells are identical anyway. But if one cell the performance degrades significantly relative to the others, then the software will compensate for that by distributing the load, typically dynamically to the other cells, and also alert the onboard diagnostic system that there, if it's very bad, that there is a dud cell, and maybe advise the user to go get that service at a time of their convenience.
So the approach is isolation, basically?
But in software, yes.
Yeah.
And load balancing across the others.
The problem with malfunctioning cell in the stack is that if you have one cell which differs from the properties from the all other cell in the stack, what might happen if you don't have a BMS which controls all the parameters in the cell is that this malfunctioning cell is completely discharged before the other cells are discharged. And as you probably know, that lithium-ion batteries must function just at limiting voltages. And what might happen that with the malfunctioning cell, that voltage polarization reverses, which could severely damage that cell and lead to the fire or explosion. So that's the reason for this. So all the cells must be equal, as Professor Harper said.
Yeah, this is, I think, probably a human psychology question. But most humans, I think prehistoric, we like margins and things. So most people, your gas tank's down to half, you get it filled. You're down to half a bottle of laundry detergent, you buy a new one. And I think people do the same thing with batteries. You know, your phone gets down to 75%, you plug it into the wall. People will probably do the same thing with electric cars. And so, and I know batteries don't like living only in that sort of top band of always being charged. Is there something we can do with either battery management systems or chemistry in the battery so that we don't do as much damage to the life of the battery by always keeping it near the top end, or am I already obsolete and that problem's been solved?
Maybe I could answer if I understood your questions well. I think that the problem is related to the manufacturers, because they want to increase as much as possible the life of the battery. And the usual ordinary consumers, they don't care if their mobile phone goes up to 100% of charge and then loses small percentage of its capacity, because in 1 year or 2 years they would change their mobile phone anyway. So the manufacturers try to get use of it as much as possible. Another possibility is try to keep the charging process well below of the standardized 100%. But in that sense, that would shorten the lifespan, and in electric vehicles, shorten the driving range of the vehicles, which might not be perceived well from the consumers. So I think that that's the problem in the manufacturers. You could build higher energy battery, it's not a problem, but the problem is how to keep it in a small volume and try to extract as much energy as possible. This is somehow yeah.
Okay, then sure have some effect, sure, but it's depending. You know, the battery cell is an electrochemical system. Is highly dependent on the temperature. Temperature is very important. So usually in low temperature, less side reaction. So temperature is very important. And the second is that the low SOC still you need to care about. Okay, too low SOC. Usually the high SOC we already do a lot of verification. High SOC is high, but still not so high. Because so high power point, this battery will have 4.2 volt. That do not mean 4.3 volt you cannot do cycling, but 4.3 volt already some fast degradation. So we set 4.2 volt. That means 4.2 you can use, no any problem. And our BMS control, no any problem. Just okay, you know, just not put your car, your battery at a very high temperature. That's okay. Others, no problem.
Yeah, when you design a car, you the usability window that you offer the customer isn't the usability window of the total battery. So you it's clearly smaller, and so you can dynamically manage that over time. The other thing I would say, and it might be interesting to get the views of other people who use EVs, is that once you trust the range predictor of the EV, as a user, I used to tend to run it down quite substantially. I'd go to at least within sort of, I wouldn't top it up unless it was about 20, 30 miles range left. So I found I changed my behavior. I would in my gas car, I wouldn't let the, for some reason I wouldn't let the tank go below, I don't know, you know, I wouldn't really like the warning light to come on, right? In an EV, if you get faith in the range predictor, you tend to go a lot closer to the wire. I found.
I have a question for Mr. Harper. Are you following the developments in the world regarding the factories for the batteries? So currently, do we have enough factory capacities or factories in construction, mines, and other facilities to satisfy some of your predictions about the
sure.
gigawatt hours in?
So I can only really talk. I can talk for the UK, and I can talk a little bit for Europe. I can't talk for other territories. So I would say, in general, in Europe, for cell manufacturing for 2030, if every one of the announced gigafactories in Europe gets built, then there will be enough cell manufacturing. Yeah. If you go upstream to active cathode and active anode material manufacturing, no, the capacity is well behind. Yeah. So, and I think that's an issue that's recognized in Europe. But I think it is a significant problem for this side of the world, and there's a lot of investment required to stand up active cathode and active anode chemicals processing, essentially. And then, as has been said before, if you go one step behind that into the mines, actually, by and large, there's enough minerals out there. I think there does need to be some more mining capacity, but it does take some time to come on stream. But I'm sure you'd be interested in knowing the Chinese perspective. So, is there enough gigafactories being built in China? Is there enough CAM and active anode?
I think in China, okay, the battery cell and pack capacity by now it's okay. And anode cathode material supply by local more than 80%, 80 to 90% already. Okay. So in China, the whole supply chain is enough, okay. But we want to do something outside China. Okay, we want to do something.
I'd just re-emphasize the upstream materials processing in Europe is behind where it needs to be.
Any other question? Until you're seeking a question, I will ask Mr. Kai. Is battery disposal a large economical problem or is not?
Recycling currently, the recycling, no any technical issue. Recycling is not so difficult. Also, your facility, we have our recycling sub plant. We have, but the current the big issue is how we get the battery from the market. This will be some difficulty. Okay, you know, battery, okay, in the end user, in the or the driver, okay, private, they have the battery. How we get the battery to our recycling plant is the channel is not so easy.
But is it technically is okay, but economically is it costly or not?
The cost in China, okay, we do some of the recycling, but for example, nickel, cobalt, and copper, and also lithium. We can earn some money in the currency. We can earn.
Yeah, I think there is a logistics issue everywhere. Actually, the recycling industry isn't really necessarily prepared to get the batteries and bring them back to where they need to be recycled. I would say in Europe, it's probably the economics are about the same. I think there is some concern about LFP batteries, whether you can get enough economic value out of recycling LFP, because it's kind of expensive and the materials don't really have that much value. But when you're recovering nickel, lithium, cobalt, then the economics are okay.
It's good, but it's really strange that it's not economic is good, but you produce all this and then finally from waste you get, let's say, economically feasible solution.
So I'm not quite sure I understand.
I mean, to produce the batteries and all of it, it's costs something.
Yeah.
At the end, you say, okay, it is still we earn some money. And
Yeah, well, right now, car manufacturers, for example, need to for every car they sell, need to put about 2,000 euros to one side to make sure they can meet their liabilities for end of life. So it is a big deal.
again, invite the audience for the question. Mario, then for you, how do you see, let's say, battery storage in buildings? Your also area is buildings, and how do you see development with batteries in buildings?
So yeah, that's an interesting thing. So when you use battery as a stationary storage in the building, you do it to, let's say, shape your signature on the energy meter such that you get some gains in terms of tariffs or in terms of power, peak power reduction, or maybe for demand response, so for flexibility. And we made some research already trying to see what would be in specific conditions of specific outer conditions, having controllable indoor climate and batteries, what would be the optimal way of operation of this whole system such that you gain maximally in terms of flexibility, in terms of cost of operation for a full day. What became apparent is that the flexibility from indoor climate is much cheaper than the flexibility from the battery, because each kilowatt hour in or out from the battery means certain degradation of the battery itself. And we need to take it into account when considering the operational costs for instance, for a particular day. Of course, in a daily scale, it's really small, but we still need to take it into account to get the full picture of costs. And so the conclusion was, for instance, if you put the optimal control algorithm to decide whether or not to engage the battery with the degradation cost we used, I don't know whether that would be the right one, but that, taking into account the cost of new battery, the number of cycles and so on, so finally you scale down what this investment in a battery finally brings to a single kilowatt hour in or out, taking into account how many cycles it can withstand. So it was the decision of the optimal controls that rather indoor climate and its flexibility in keeping the temperature within plus minus, let's say 1 degree range within a certain set point is much cheaper to assure both flexibility and optimal operational cost. So battery was not used unless we put the degradation cost on a really small level. But hearing about 18,000 cycles of a battery, that's something completely different. Then of course this battery is coming with its kilowatt hours in and out with a much smaller cost, and then it gives finally the price in terms of the praise, let's say, in terms of flexibility you gain. So with the battery we were considering, and the rather, let's say, modest life cycle and number of cycles, it was really predicted to rather not to be used in a building, although it was there, but rather make your flexibility, make your, let's say, make your peak power shaving with other systems and not with the battery. Okay.
Thank you. And Professor Mandic, let's say, how do you see sustainability of large number of using of batteries? Any batteries in general.
How do we look at sustainability? and that's related to the efficiency of the cell, and the chemistry of the cell. So, we need to improve the cell chemistry in a way that make the cell more efficient, to have better coulombic efficiency and to have less degradations, so which has been already mentioned here. And we could achieve that by improving the materials and to improving the energy losses within the batteries. So there is, in fact, there is a huge amount of money which are funded just for for the purpose of making better cells and making them sustainable. And one direction is to invent new materials or a combination of existing materials which would achieve higher voltages or higher charge densities, which in combinations give us more energy density. And another way is to, from the electrochemical engineering perspective, to try to minimize energy losses as much as possible. And this is by overcoming all the over voltages which occur during the battery operation. So this is something which electrochemists and electrochemical engineers do together with the material science and material scientists who want to make better materials. So in the future, there are a couple of directions, and I believe we might reach better sustainability, longer driving range, and longer lifespan of the batteries. But we'll see what the future holds. I'm quite optimistic, but the numbers I just said that Dr. Kai mentioned are quite impressive, but I think that the practical values now are rather lower than this. What the values and the performances which now exist in the commercial market.
One question for Mr. Kai. Recently in many newspapers really now was comments that in the European Union that China will soon dominate the sale of electric cars in the EU. How do you see this? This is real in newspapers.
You know, I'm just a scientist, okay? No, that issue. I think, okay, it depends on if you pay emphasis on it, it will get improvement. It's no any problem. Just, okay, in China, okay, from the government to the company to the people, okay, they do a lot of the effort, okay. They like use the EV, then some policy say they can get the benefit from the EV. So we do a lot of work. So gets a lot of EV cars. But as in other countries, okay, if you do the same, will be had the same result. No any problem.
Main comment was that the main problem for electric vehicles is it's more expensive than normal cars today. But that China reduced the prices, and for that is, let's say, these comments that probably you can dominate, and that ordinary people can buy electric vehicles from China, what is not now possible from European Union. It's really so much expensive that it's in Europe. What was asked before to the guy from Germany, why European is delaying with development of electric vehicles, all of these very famous, let's say, car producers.
I would just to add here that the Chinese electric cars will surely dominate the European market unless political administration does not interfere. So That's the trend, and for Europe it would be very difficult to compete with the Chinese manufacturers in terms of price, maybe not in terms of quality, but in terms of price, yes.
Yeah, so I'm just an engineer, but I do work for the UK government. So my view on this would be that there's some fantastic products coming out of China. Really good quality is very good. Price positioning is very good. But we are also seeing some regulatory moves in this side of the world that might try and make the playing field a little bit more even. So for example, when UK left the European Union, there is something called the Trade and Cooperation Agreement between the UK and the European Union, and part of that agreement says that in order for vehicles to be traded tariff-free between the UK and Europe, by 2027, 65% of the value of the battery will need to originate either from the UK or from the European Union. Yeah, so that is an example of where regulation is going to try and kind of balance things out of it, and I think we'll see more of it on this side of the world.
And there is no more question for audience, and one more, Goran.
Just a short one. You showed that there is a space for improvement in batteries. So what is your opinion on the learning curves or let's say, learning rates? Shall we keep them until now, or there is a progress from improvement? Or let's say we had the reduction of price 80%, so is it more space to do that?
Maybe I'll start, and then I think as Kai showed earlier, the progress from 2012 to 2018, 2020 was very, very, very quick. Yeah, but you could argue those were easy wins. I think the rate of, I'd say the rate of scientific progress, the rate of engineering progress is kind of speeding up. You know, the tools that engineers and scientists have now to help them with their work are much better than they were 10 years ago. And the number of engineers and scientists that are dedicated to battery technology development is much higher. However, the difficulty in solving those problems that we talked about earlier to generate marginal increase is getting higher. So marginal increases are requiring much more engineering breakthrough in order to achieve them. Yeah, but you know, progress is being made. We've seen it at the cell level, but also it's being made at the pack level, and is being made at the software level as well. And we're getting quite close, as hopefully you saw in my chart, to most transport applications being well served by the performance of battery technology. And I think somebody just mentioned, I think the emphasis now will be, on this side of the world, will be on cost. How do we keep that performance but get the cost? How do we drive the cost down? And we need as much innovation on cost as we do on performance improvement.
Okay, for the current the battery and chemistry, one is the lithium iron phosphate, another is NCM. These two, okay, we still have some optimization room, still have. But just like Mr. Harper say, okay, just this curve, okay, cannot be that one. For the cost, you know, it largely depends on the raw material. For example, how is the lithium come outside, that's price. So, or the manufacturing, the cost, okay, a little bit to almost stable, almost. But still, okay, some new chemistry, still, we have some room for some new chemistry. For example, NA, that kind of NA battery. For example, some new, even all solid. For example, our condensed battery is something. You see, if we have some the chemistry breakthrough, we have some big room to improve.
At the end, I again give each of us, if you have something to add that you not mentioned before, if you need to add something.
Yeah, I'm not sure. I think we've covered a lot of ground. Maybe the only thing I would say again, because we've got a lot of academies in the room, is to emphasize that point I made on skills right at the end there. So, we need our scientists and engineers to be much more multidisciplinary to solve these problems and to move things forward. Whether it's incremental or breakthrough, you tend to need electrochemists and people who are comfortable with AI, people who are comfortable with software development, and as I said, with system optimization, you also need to combine all of that knowledge with mechanical engineering, thermal engineering, structural engineering, and all sorts of other things as well. So I think the last thought I would give is don't forget that we need, in order to address this significant transformation, we need to think about how we are training our next generation of scientists and engineers.
Yeah, this is a very good message to all these academies.
No, I'm just conclude as the same as Professor Harper.
Then we should thank all the panelists. I think it was quite interesting.